So guys, I think we can start.
Okay, we can start. No issues.
So good evening all. Welcome to third day of Adult Online FDP on Smart Energy Storage Technologies from Research to Real World Application, organized by Department of Electrical and Electronics Engineering, Government College of Engineering, Kannur. So today we are delighted to have with us Professor Shaijumon MM, Professor and Head of the School of Physics at IISER Trivandrum. He obtained his PhD in physics from IIT Madras and has reached international research experience as a postdoctoral fellow at Rensselaer Polytechnic Institute and Rice University in the USA, and as a doctoral research at University of France. Professor Simon's research focuses on energy conversion, particularly in the development of advanced batteries and supercapacitors. He heads the DST IISER Trivandrum Center for Solid State Battery Technology and has over 100 research publications along with multiple national and international patents. He is a recipient of several prestigious awards, including the DAE Young Scientist Award, MRSI Medal, and Research and Technology Awards. So we are
Yeah, thank you very much. Thank you very much, Akhil Chako, and also to Dr. Sugesh, a very good old friend. It's been a long time. I happened to meet him, in fact. But thank you very much for this opportunity. It's always nice to interact with teachers, college teachers especially. So let me just share my slide here, and then. I hope my slide is visible.
Yes, sir. Yes, sir.
Okay. Okay. And my video is still on, I believe. Sometimes it just gets switched off.
Yeah, it's on. It's on.
Okay, great. I think we'll start. And Dr. Sukesh, I think what was the plan? We break for some time. Is that what time? And
yeah,
maybe...
it depends on your convenience. So whenever you want to break, you can break, and we'll have a short break. Or else, if you want to continue throughout, it's also fine with us.
No, maybe we can give a small 10-15 minutes break in between. So
okay, so you just let us know when you want to break, and we can.
Okay. Okay. Okay, that sounds great. Yeah. All right. So very good evening to everyone. So it's a great pleasure again, as I said, to talk a bit about what's happening in battery research, right? Specifically looking at, and first of all, I think I should congratulate the team here for organizing a program like this, faculty, the program, development program, specifically with a theme on, energy storage like this, right? It's certainly getting so relevant these days, and especially when it comes to the batteries. Absolutely, it's so relevant to the society that we talk today, right? So what I thought is, and I've been told that there've not been any battery talks before, so I thought I'll just probably go through some of the fundamentals and just give you a sort of overview of what are the current trends in the battery research today, right? So that's the whole idea. And then I'm sure most of you are, I believe, almost all are from the electrical engineering or electronics department and background, in fact. And I'm sure, I mean, I get to meet a lot of people from this background, in various colleges, because I sit in some of these committees these days, and get to meet a lot of people from electronics and electrical background who've been working in this area of e-mobility, vehicular applications, right? Mostly looking at the BMS aspect and other things, right? I do collaborate with many of the people from this background as well. We have long time collaboration with the CDAC in Thiruvananthapuram. So we're working very closely on the Kerala government e-vehicle policy. We have a consortium here where we are also part of that. So once again, so let's just move on. Before I move on, I would just wanted to take a couple of minutes. I don't know how many have been to this campus in IISER. There's a very beautiful campus in Trivandrum, one of the beautiful campuses across the country, I would say. This is in Vehicular, about 35 to 40 kilometers from the city, and it's a wonderful place. And please feel free to visit us sometime when you're around, right? So that's I would start with that. And to those who have not much information idea about these institutes, these are premier institute, in fact, very similar to the Indian Institute of Science, Bangalore. And we have 7 of them across the country, as is listed here. And ours was formed much early in 2008, in fact. And yeah, so the focus is mostly on basic sciences here, though we have started a couple of departments else. Other than that, especially we've recently started data sciences. Some of the IISERs have started computer sciences, and even economics also has been started, sort of slightly widening the scope and things like that. All right. So again, we have a very active research going on at IISER, where we've been working on multiple things, and any technology for that matter, if you take, right, be it your own technology, electronics technology, right, advanced electronics technology or battery technology, any technology for that matter, right? I think materials play the key role, right? So there's a very famous saying, which those who control materials control technology. And we also work quite a lot on materials of different kinds, different forms, two-dimensional layered materials, all the way from graphene to beyond graphene. I'm sure some of you might have already known about or might have been working on similar systems like molysulfides, tungsten diselenide sulfides, and things like that. Quite exciting materials for its physics, as well as for various electronics and other applications as well. So we work quite a lot on these materials of different forms. That's one aim, that one of the goals that we have. Just take this pointer. Yeah. And yeah, so the other major share, the major interest lies in batteries. And the theme is sort of energy and environment. So batteries play a very key role. And this is something we've been working over the last 20 years or so, right? Catalysis to generate hydrogen, which is again another key area in this whole direction, right? And we also work on developing some porous materials which can capture carbon dioxide in a direction to sort of help the environmental issues, right? So this is just the background on what we do. And let me also start with acknowledging a fairly large group at IISER, comprising of master's students, about more than 10 PhD students, about postdocs and various other levels people. And we've been so blessed to have funding from various agencies as listed here. So let me also take this opportunity to thank them, both both the government level as well as the industry supports that this quite been really beneficial for our research. All right, so what I've planned for today, as Dr. Suresh was mentioning, maybe we can just have a small break in between, whenever and wherever we can stop. I would probably stop there. But essentially, the idea is basically to give a sort of an introduction to the electrochemical energy storage, right? And very specifically looking at the lithium-ion batteries, yeah. And I would go and try to convince you that, look, the existing batteries that we have today have a lot of issues, which most of you are, you know about it. So we'll probably look into what are the performance issues in batteries, right? And that's where we talk about building better batteries, right? When you want to build better batteries, what are the challenges that we go through? Is it the materials alone challenge? Of course, materials has always been a challenge in battery technology because, as most of you know, there are several companies, there are several industries, several startups in India claiming that they are manufacturers of batteries, lithium-ion batteries today. But take my word for that. As of now, there have not been any single entity, any single industry in India, who are doing from the scratch. It's all materials either comes from China, or the devices as such comes from China. All that they do is, assemble these kind of things, put it in your, automobiles, and then claim that you're battery manufacturers. Unfortunate, right? So there has to be a sort of a revolutionary change that has to take place in this, right? In order to sort of get to the dream, right, of this, getting out of this independence, coming up with this independence on this material. So, of course, these are important performance metrics. On the later part, I'm going to touch upon the various advanced systems, right? Or most of you by now will be familiar with what are lithium-ion batteries. And then there are reasons to go beyond, think beyond the lithium-ion batteries. And there are various options, choices out there, right? All the way from sulfur batteries, the sodium-ion batteries, the counterpart. And there's something called anode-less, exciting. That's sort of a cutting edge in the battery technology. And of course, moving towards this solid-state batteries, right? And I will also touch upon very, very bit on battery recycling, because now it has already started, and it's going to be flooded with batteries, in the years to come, right? And maybe in another 10 years or so, nobody knows what we are going to do with the existing batteries. Now you can see vehicles running all across, right? Automobile, the two-wheeler, three-wheeler, four-wheeler running with the batteries. All are excited, but then down the line, another 10 years, we still don't have a plan. What are we going to do with this cycle batteries, right? Maybe it goes for another 10 years, right? It's all going to be dumped at some place. What are we going to do with that? Can we recycle it, right? To extract the elements from it and try to sort of, repurpose it or recycle, reuse it for something else, right? That's very important. So that's something, if time permits, I would just touch upon. And pretty much we work on, all these things in our lab, right? So that's something of very close to my heart. So once again, let's just move on with that, right? Okay. On a very broad thing, I think this is where we should start, and where we, have to do something, because we all are aware of this danger, right? The environmental pollution, and which is sort of causing the whole issues, all over, right? So ultimately, the renewable energy is something that all of us are looking forward to, right? Absolutely, solar is undoubtedly the richest source of energy, but then towards powering a future. But then these are all intermittent energy sources, and you cannot depend on this all the time, right? And that's where we talk about storing energy, right? Storing electricity in whatever form that we can, right? So that's where the importance of energy storage get into picture, right? And when you really look at the multiple ways of storing energy, it could be just the batteries or the electrical energy storage, right? In terms of batteries, capacitors, supercapacitors, right? And and even hydrogen also one could store. It's another form of energy. It's an energy carrier. So basically categorized into chemical, electrochemical, electric, and mechanical, right? Even thermal energy storage, most of you might be familiar with that, right? So these are some routes to store electricity, store energy, in fact, right? But what we are interested is mostly on storing electricity, right? So the two important approaches or ways or methods to store electricity is the following, that most of you might be familiar with what is called as supercapacitor. In fact, it is a sort of a celebrated version of the capacitor, the dielectric capacitor, right? Where you have two parallel plates, right? And separated by a dielectric. So charge is basically stored on the surface of these metal plates, right? The only difference here is you're completely transitioning to an electrochemical medium, wherein you have a highly porous electrodes as the cathode and anode. Typically, these are porous carbon, right? And of course, there is a separator and there's an electrolyte. So when I say electrolyte, it will be simple NaCl for that matter, Na plus and Cl minus, and then you have two electrodes. You just apply a bias, the electrodes get polarized, and the respective ions, positive and negative ions, move towards the respective electrodes, and a double layer capacitor is formed at two ends of these electrodes, right? That's what we call it as a supercapacitor. The word super is because the capacitance that we get from supercapacitor is quite high, right? We're talking about microfarads in terms of the dielectric capacitor, and we are talking about tens and hundreds of farads. So that's basically the difference, right? Now, I'm not going to talk much on that, but just a couple of differences between this versus the typical rechargeable battery, in particular the lithium-ion battery, as is shown in the right-hand side, right? You do have an anode, you do have a cathode, current collectors, an electrolyte, separator, which is part of any electrochemical device for that matter. Yeah. So what is the basic difference between the two? As I said, the understanding from a basic dielectric capacitor, we know that the charge is stored at the surface. Same goes here as well, right? Which also means that the rate capability or the power density is quite high here because it is just stored on the surface. So whenever I need it, just reverse the potential, I get everything quickly done. Charging and discharging is very fast. Whereas in the case of batteries, lithium-ion batteries, the capacity, you have certain limitations because it is the mechanism of storage is slightly different, right? It is electrochemically stored, and it is of redox in nature. There are diffusion of these ions. Say, for example, lithium ions has to pass through and get through this material. So accordingly, the energy density also is going to be slightly different, and for that matter, batteries are having higher energy density, but the power is quite low. There's always a trade-off between these two, right? So coming to lithium-ion batteries, why are we so interested in lithium-ion battery? You get to hear only lithium-ion batteries these days, right? It has become so dominant in the market today, right? A couple of very simple reasons for that. You look at this interesting plot here, wherein the energy density, the volumetric energy density on the y-axis is plotted against the gravimetric energy density, which means the per weight, energy per weight, and energy per volume. It's a very important measure. It's a very important metric or parameter to measure the performance of a battery. And you could very well see that, right? Lithium-based batteries sort of very well outperform the other counterparts like lead acid, nickel cadmium, nickel metal hydride, any other chemistry for that matter. Primarily because of its lighter weight, and second is because of its high electrochemical potential. You are getting around minus 3.04 volt versus lithium, right? Versus RHE for the lithium ion, and that puts at a very, very sort of high position in terms of its performance, right? And that's precisely the reason why these three gentlemen have been awarded the Nobel in Chemistry in the year 2019, and for the development of lithium-ion batteries. And this is a very, very interesting point I typically make, because it very clearly tells how do we work together, right, in a very interdisciplinary manner. The very fact that mostly the people with electronics or electrical engineering background, the faculty members listening to a talk on batteries, talk on battery chemistries, physics and material science of batteries, that tells it all. Because look at these three gentlemen, right? All the way starting from John B. Goodenough, right? It's basically a theoretical physicist who moved on to Oxford to chair the department of inorganic chemistry. And this person who's solely responsible for developing the cathode, the lithium cobalt oxide cathodes in these batteries. Stanley Whittingham is a chemist, right? Who've been also working on the anode side and the TiS2 based batteries, paint-based electrodes. And Akira Yoshino is a engineer by profession. So he's the one who basically came up with the idea about the graphite as the anode. So look at how wonderfully these three people from three different backgrounds came together, and it's a very clear message to be given, right, to the present community that you need to have these sort of people coming together. There are multiple forums that are happening, right? Most of this funding that's happened today is of multi-institutional, multi-PI, disciplined programs are happening, because it is so it turns out that it is essential these days, right, to have a interdisciplinary approach to solve such a big problem, right? It's just the physicists or the chemists or the electrical engineers alone are not able to sort of come up with these solutions to much of these advanced problems and challenges that we get to see, right? Just a note on this I thought I would share. Coming back to batteries. So, if you were to cut open a battery, a lithium-ion battery in particular, right? This is a fair sketch that you get to see in a battery, where, as I said, you have a current collector, you have on both sides, anode as well as the cathode, and you have this, the anode materials, the cathode materials. I'm going to tell one after the other. So you can see that these spherical particles, this one on the left-hand side, these are anode particles. Of course, these are cathode particles. And then, there are a couple of things. You can see this blue background, which sort of binds together these particles, very important. Otherwise, particles gets, separated. So there has to be some glue, right? We call it polymer binders. PVDF and certain other things are examples. So these are used to bind the particles. And most often, especially the cathode materials, most often these are electronically not very conducting, right? So that's why you get to have these kind of black connectors here, which are typically called as binders, electronic binders. It could be carbon for that matter, activated carbon or super P carbon, right? Which binds together these particles electronically so that they talk each other. Otherwise there's a problem. Yeah. And of course, there is a separator here, which is sort of drenched in the electrolyte. So that's the basic picture of a battery, right? Little closer, if you look at it, the present day battery is something like this. You have a copper current collector, and you have this graphite as the anode, which are sort of layered materials, right? And on the cathode, we have lithium cobalt oxide. Interestingly, this is also a layered material. And you have an aluminum current collector. There is a reason for why I specifically mentioned aluminum on the cathode side and copper on the anode side, because I cannot put a copper. I would have loved to put aluminum at the anode side, because economically it's quite viable in terms of, compared to the copper. But unfortunately, if I put aluminum on the left-hand side, on the anode side, that aluminum is going to react with lithium at that particular operating voltage. And that's the reason why aluminum cannot go here, whereas aluminum can go here, because at that particular operating voltage, high voltage, aluminum does not react with lithium. Right? Vice versa, I cannot put copper here, which I don't want to put, but I cannot put copper here because at this voltage of active operating voltage, lithium reacts with copper. Anyway, that's a different thing. So what happens, the very basic working principle in a lithium-ion batteries goes something like this, right? When you buy a lithium-ion battery, these days it comes with fully charged, right? In a completely discharged way, what I have is just a graphite on the anode, and here it's a fully packed lithium cobalt oxide. When I say fully packed lithium cobalt oxide, this little green spheres that you see, which is sort of intercalated or lies between these two layers of cobalt oxide. These are the cobalt oxide layer, and these green ones are the lithium, right? Sort of sandwiched between the two layers. So that's the lithium cobalt oxide. So, I have to charge the battery initially. And when I say charging the battery, right, it is sort of an oxidation here happening, because what happens is like, lithium cobalt oxide is releasing this electrons and the lithium from here. So this electrons cannot go through this medium because it can only permit lithium ions. So the electrons will take the external path. So when you're charging it, that's what you get to see. The electrons will take this external path and it gets to the anode. In the meantime, the lithium ion travels through this liquid electrolyte, because thankfully you have a porous separator. It can be just a piece of paper, right? So it goes through it and lithium gets to this anode material, and this carbon combines with this Li plus and this electron which is coming through the external circuit to form a complex, something called LiXC6, which means like 6 carbon atoms get hold of one lithium to form this complex LiC6, right? And when it is sufficiently charged, when I say sufficiently charged, the entire lithium cannot and will not go to this place, because what happens is only around 0.5 lithium alone will go here, because more than that, if it goes, this structure collapse. So it is so designed that much only lithium will go here, right? Otherwise the structure will collapse. So whatever it is, so if it's fully charged, we call it the entire lithium is now onto your anode side, and that's the stage where we call it a battery is fully charged, right? And the moment you discharge it, meaning you started using it for your mobile phone or lighting a bulb, again the reverse happens. Oxidation happens here, whereby lithium ion and electrons are released from it. Electrons take the outside path, whereas lithium ion go through it. Combined here gets reduced here as lithium. And while these electrons are flowing, that's where you get to see, your working of your bulb or whatever it is, right? That's a very simple understanding of how a lithium-ion battery works or performs, right? Now, of course, moving on, there are different types of batteries, starting with the primary batteries, non-rechargeable batteries, right? And the lithium-ion or the rechargeable batteries we talk about it. Of course, these are all quite known to all of us, so let me not worry too much. But just a quick point that non-rechargeables are still being used, right? These are typically for places where heart pacemakers, defense applications, oil drilling, where it is not very easy to recharge often, right? These are the domains that we basically use this sort of non-rechargeable primary batteries, right? Or otherwise, we get to use that. And this is one area, in fact, right, is getting changed, right, thanks to the new advancements in technology. And we are literally looking to some sort of mechanism by which, one could charge these batteries, right? Even at places which otherwise it's difficult to, for example, even pacemakers for defense, people are trying to do that, right? Electromagnetic induction and various other forms of, there are means of charging these batteries nowadays. Anyhow, the construction goes something like this, right? So there are cylindrical, there are coin cell, thin film, prismatic, all sort of battery modules are available these days, right? Depending on where to place, what to place, how to place, it vary. All right. Now, from the understanding that we have on the mechanism of storage, let me just take you to this very, very important and interesting slide, which is a plot actually. This is if you can understand this pretty much, I mean, you pretty much get the whole essence of this batteries, because what I'm showing here is simultaneous process that's happening in a battery. For example, when I say you have an anode and cathode, I said lithium ion comes from the cathode while charging and gets to the anode and forms a complex there, right? So while these lithium ions are leaving this cathode and entering this anode, different processes happens at both ends, right? So that's what you get to see here. The blue line stands for the reaction which is happening at the cathode end, wherein you can see that, let's say I'm charging the battery, the lithium ions are moving. Getting charged means, you see, there is a potential here, there's a voltage plateau here, which is corresponding to this reaction, which I said, lithium cobalt oxide, releasing lithium ion plus electron, plus leaving the cobalt oxide layer there. At the same time, these lithium ions are moving through this, the separator and electrolyte and getting intercalated into this sheets of graphite. And that process is being shown in this sort of a pink plot here. Right? So which means like these two processes are happening simultaneously, and there is a voltage at which this lithium cobalt oxide, this oxidation happens here, this reaction, and there is a voltage at which this reaction happens, where the intercalation of lithium between these layers happens, and that is very clearly marked here, around 0.2, 0.3 volt here, and around 3.9 to 4.1 volt here versus lithium. And just to give you the idea that what is the source of this voltage that we talk about, all of us, I don't know how many of you know that the voltage of a lithium-ion battery is about 3.6 to 3.7 volt, right? Compared to what we know about 1.5 volt for other batteries, right? So what's the source of this voltage? It's very simple. It is the difference between these two operating potentials at any point of time, right? So you have around 3.9, 3.9 to 4, and you have around 0.3 to 0.4, which gives you an average potential of about 3.6, 3.7 volt, right? So now my point is that you might be wondering, right? I wanted to increase the energy density, and that's the cry that's going on, because now you're talking about large scale applications, for instance, the e-mobility, the vehicular applications. So far it has been okay, because we've been doing with a mobile phone, or charging your laptops and things like that. Things have changed. Now you're moved on with electric vehicle applications, which is demand is so high, right? And we're still worried whether we are able to meet that demand at all, right? So essentially, I wanted to have my battery getting or giving larger energy density, higher energy density. And energy density depends on your operating potential and the capacity, right? So it's very simple, because as I said, at any point of time, the voltage difference between these two curves gives you the voltage of the cell. So if I wanted to increase my voltage so that my energy density can be improved, very simple, why not I make some materials which will give me a voltage of high voltage than this? Or why not I think about some anodes which give me a voltage lesser than this, below this, so that my voltage window is sort of expanded? Sounds very simple, but then there are issues, and that is marked here by this yellow patches, right? Because I cannot go beyond this, because you're using a liquid electrolyte here. So if I go beyond this dashed, the mark here, the electrolyte will decompose. It oxidizes, and it releases some gases, right? And when I say it releases some gases, then finally what will happen is it just gets blown up. And that's what you get to see here. You keep charging, repeatedly overnight, you can see that the battery sort of start bulging, right? Because there is some gas evolution has happened, and that's why the battery gets bulged. And finally, it would blow away. Okay, can I then go down? Answer is no, a big no, because again, here is the dotted line. If I go beneath that, what will happen is lithium, instead of intercalating in between these graphite layers, it would start depositing as metallic lithium, which is dangerous, because if the lithium starts depositing, it will start creating something called a needle-like structures, which are called dendrites. I have a better slides later on, which I can explain further. But just take my word for that, these are dangerous, right? Because these needle-like creatures can pierce through your separator and short your battery, blast. Okay, so these are the major issues I just wanted to bring your attention to. The challenges that we talk about it is not very easy, right? Unless you really work on various components of these batteries. So my challenge slide starts from here, in fact, right? And of course, there are multiple materials which are out there, right? Be it in the form of various carbon alloys, intermetallics, even lithium metal itself, which I'm going to talk to you a little later, at the anode side. At the cathode side, different oxides, electrolytes, those who are good in chemistry, yes, you can play around with the various kinds of electrolytes for that matter. But then the point here is it's something like you walking into a kitchen and then you get to see a lot of these ingredients, right? The right mixture is the key point here, because if I choose a particular anode, might not go well with the cathode, and the electrolyte compatibility would be a problem. So you want to really choose the right material out there and sort of optimize your performance of the battery. And this goes on, right? So for a typical user like us, right, what is more important? How do I select a battery chemistry? Absolutely, there's no second thought, because cost comes first, right? The lifetime. I mean, I would just ask this question, right? How long I can cycle my battery? Can I cycle forever, right? Abuse tolerance is a problem, and of course the performance. Right? These are the 4 criteria we use to select or grade a battery chemistry, right? And there are these indicators, right? Of course, as I said, safety important, cost, and battery life. These are something that all of us are, worried about, for that matter, right? So these are some terminologies which I will be quite often using in the rest of the slides, like specific energy, which sort of tells you what is my range. When I say range, it's all connected with my e-mobility or the vehicular applications, right? The more the energy density, more I can talk in terms of the vehicle range, mileage. Then power is linked with acceleration, as you know, right? So the more power is important, especially when you're talking about the vehicular applications, to accelerate, to start the car, to accelerate it, it also requires this power, right? And there is something called C rate, which is the current at which the battery is fully charged in an hour. Then state of charge, depth of discharge, as is shown here. These are some important terminology that we quite often use. All right. Now, many of you have probably gone through this nanomaterials, right? So when I talk about materials, nanomaterials, and people talk about why don't we use nanomaterials in batteries? Good and bad. There are issues, there are positives. So I would just start with the positives of this battery nanomaterial being used in energy storage. So assume that no nano, you have some bulk materials which are used to make anode and cathode. So when I say the performance, you can see that the lithium has to basically really struggle in terms of diffusing through the bulk of this cathode material, because it has to really come through the bulk of the material. That's what we call the rate determining steps. And it comes out, then you can see that it's a sort of a swimming pool, because you have a liquid electrolyte there. It can very fast swim through it and gets to this anode. And there also it undergoes this diffusion throughout the material. So it's quite hard, and that's where you sort of fail or have some issues with your power densities. What if I'm going to break down this bulk material into very tiny particles, right? Keeping the same material, but then crushing down into fine particles, let's say into nano range, 10 to the power of -9 meter, right? As is schematically shown here, compared to this bulk, this is going to give us much relief in terms of its ionic transport, because now lithium ion can kind of get transported or can kind of move much faster. The rate performance would increase because of this presence of nanomaterials, right? What if I have a electrode which is made of fibers or which is made of tubes, nanotubes? It's something like a national highway for these lithium ions. It can very fast, it can traverse, right? So I hope you get the difference all the way from bulk to nanoparticles to something like nanowires or nanotubes. So essentially, these are going to improve your electronic transport, sort of giving you a much higher power capability, right, when you're using it. So these are the positives. Well, if you ask me, the negatives are equally out there, because nano is not that great, because especially for batteries, because any material, if you bring down the size of the particle, the reactivity of that particle is going to increase. For example, if I have a bulk material of copper or nickel, I thrash it down to something like 1 to 5 nanometer size. Look, the number of atoms which lie on the surface are going to be larger. That's what we call it as surface to volume ratio, are going to be larger than the number of atoms which are in the bulk. And as all of you know, because the surface atoms are quite reactive, right? So bringing down the particle to nano is not always good, because it also brings a little bit of reactivity for the particles, and any sort of reactivity is sort of killing for the battery, because there could be sort of irreversible reactions, because I don't want that to happen, because lithium ion, according to me, should just be a very obedient guy and should just get into intercalate in between the graphite. It should not worry about anything. So being a nanomaterial, these are distractions to the lithium, because nanomaterials are reactive and lithium tends to react with the nanoparticles, right? And by means of which I'm going to lose some lithium ion, because the moment the lithium ion reacts with these nanoparticles, these are not going to come back. These are irreversible. It gets tied you up. It will not release the lithium ion reversibly, right? I'm going to lose my lithium there, which is going to affect my cyclic stability later on, right? So these are some issues when you use nanomaterials. So yeah. So this is something very, very dangerous, right? Because all of us, especially your kids, very happily will hand over your mobile phone to you when they get to see this screenshot, right? We'll be happy with the handing over, but you can see that they're handing over to sort of asking you to sort of recharge the mobile phone, right? Dangerous, which we don't want to see at all. What about this? This is a odometer in an electric vehicle, right? Imagine you're driving in the middle of nowhere, right? And suddenly, all of a sudden, your meter starts alarming you. Look, hook me up somewhere. I'm going to die out soon, right? No charging stations around, right? And this range anxiety is something killing, right, among the proud users of the electric vehicle these days. Yeah. So it's even more serious, compared to the one which I showed earlier, right? So what does it mean? What does it mean? Because you really need to have a lot of performance improvement brought in, which I'm going to talk to you a little later. But just to touch upon a few other things, so far we have learned about how does the battery works, and we talked about storage of different kinds, capacitor storage, battery storage, various other storage medium, right? Especially when you look at batteries, it is interesting to note that storage is needed at all scales. When I say scales, right, the application domains, right? We were all happy at some point of time where this, as long as my portable electronics works, as long as I have enough supply of electricity to power my mobile phones, to power my laptops, I'm okay, I'm happy, right? Things have slightly changed in the recent times because some of us, right, are started using electric vehicles across. So then we get to worry. That's the range anxiety that I mentioned now, right? You get to worry about in a little bigger way because whether the batteries that you talk about can really support me, right? Can really save me, can give me enough mileage. Yeah. But then I just want to mention you that there are extreme domains, extreme ranges of the use of these batteries. For example, backup power, grid power. I'm sure being from the electronics, electrical engineering background, you know what I mean by, right? The power grids. And there is, people have been really looking at storing electricity in this forms of big backup power grid storage, right? Wherein an entirely different architectural design, materials design is required, right? Even though you're using a very similar material in all these domains, right? The material design, the way you stack your materials will be different, right? And there is a very extreme end at this lower end on the micro scale or nano scale, right? Which is even interesting, right? I mean, all of you would agree with me that, you know, the advancements in electronics industry has been quite, has been great, isn't it? Right? You think about it, you can actually come up with a very, very tiny device, be it a micrometer device or even a nanoscale device. You can come up with that. Absolutely no problem, right? But then, if these devices have to be, unless these are self-powered, right? Unless these are self-powered, forget it. Because as of now, at this moment, right, you do not have a battery on board these tiny devices. What I mean is, we don't have a nanoscale battery or a micro scale battery even, right? There's a huge research gap at that extreme regime, right? So the question is, can batteries power tiny devices? And that's exactly what I said, right? You talk about MEMS and NEMS devices, right? You are in a very comfortable stage where you can think about, miniaturizing the electronic device. Unfortunately, the battery the battery technology is so laid back, right? It has not got to that stage of miniaturizing these power sources. Had that been done, think about this pacemaker, simple example, right? Believe me, 3/4 of this pacemaker is consumed or filled with a battery, right? So I'm sure you would agree with me the fact that leave apart the battery side, the entire electronics, the entire other components in that pacemaker can be shrunk to very, very tiny area. It's just that the battery needs 3/4 of the space is sort of unfortunate. So can we not come up with a very, very tiny device, okay, very tiny battery, right? Otherwise, these biomedical micro machines, you would have heard about this popular thing that can you think about a micro device, a biomedical device that goes through your blood vessels and attack your cancer cell, whatever, right? I don't know whether you have thought about this, because unless these devices are self-powered again, forget it. There are not such batteries available in the market today which can be on board these tiny devices, right? You might counter, the question would be like, why not we use a thin film, battery, right? A solid state thin film battery. Unfortunately, when you do the back-end calculations, energy calculations, it turns out that the thin film micro batteries fail to fulfill the needs. When I say the needs, the energy and the power needs, right? So just to cut short, we are talking about something like a thin film battery here. And the only way out is to move into sort of a three-dimensional substrates or a 3D form for the battery. I will just give you a very simple example. Imagine you have a land, let's say 1 cent of land, right? That too on the side of the national highway, right? Just 1 or 2 cents of land. And you have to build a house. And when I say building a house, I'm very particular. I have to have 4 or 5 rooms because to cater to my family, larger family, right? But you have just 1 cent of land. What do I do? Right? What do I do? And this is precisely we get to see in terms of electronic devices, because the idea is basically to miniaturize the device, and the electronics engineers like you would come up with a very, very tiny design footprint and fill everything and tell the battery people, look, I have only very limited footprint for you. You place your battery there, but remember, it has to power this device. Exactly what I said, the analogy, right? So what do I do with the 1 cent of land to have 3 rooms, 4 rooms? The only way is basically to build vertical, right? That's what you get to see here, right? Build vertically, go up with a very limited footprint. And that's the only way out when it comes to miniaturized power sources. Okay, very tricky problem, very challenging. So how do I make these kind of 3-dimensional architectured batteries, micro batteries, right? If I were able to do that, it would be interesting because it would have both energy and the power density quite high, right? And again, just to clarify your doubt, you might be wondering, right, these tiny devices, what am I going to do? How much power density, energy density that are you talking about? Well, if I get a couple of hundreds of, let's say 100 to 200 microwatt per centimeter square power density, I'm happy because that's the domain that I'm talking about. This is to support a very, very tiny device. I'm not going to use a micro battery to power my mobile phone, right? That's what I said, the energy domains. Depends on what domain that you're talking about when you're applying these batteries. Batteries can be of the same type. When I say same type, the chemistry, the anode is graphite, the cathode is lithium cobalt oxide. No change in that, but then the architecture is going to be different because here it has to go in a vertical manner, right? So that's what I meant to say. And that's where the material science gets into picture, right? How good you are in tuning the materials properties matters here in a big way, right? So a lot of applications on micro batteries, the market is shooting up, right? So can we think about something like an interdigitated pattern, right? Starting from a copper, plate and use the advanced lithography techniques, right, to engineer this material, to make these tiny structures like this and build the entire battery in a way that I told you, in a moving vertical, right? It's a very exciting field. In fact, a couple of my students are working on it, thanks to various techniques available at IISER in terms of lithography, e-beam lithography, and things like that. We're able to progress in this one. So ultimately, right, these are going to be very, very tiny device, so to speak, right? All right. And of course, on a larger scale is about the vehicular applications that most of us are sort of excited about it. And the game is completely different here, right? Even though you're talking about the same material, right? So talking about e-mobility, of course, I think, there's been a lot of policies, there's been a lot of initiatives across the country in terms of the e-mobility. As also, there's a national e-mobility program which has come up. And idea is very simple because, looking at the energy consumption, right? You can see that it is predicted to go down as is shown here. At the same time, the CO2 emissions, because multiple things are happening at the same time, and you're also going to address the CO2 emissions, right? It is also expected to go down in a big way, right? So there has been a lot of initiatives, and I'm so proud to say that Kerala government, Kerala is one of the states with started thinking about this e-vehicle policy in a much ahead than compared to other states, and we do have a e-vehicle policy in place. And there is an initiative run by the KDIS, and there's a consortium on e-mobility among the various other partners. IISER is also, I'm proudly mentioning this, IISER is also a partner for that, and we are on board to come up, and a lot of things are happening. There is a electric vehicle park which is coming up very recently is going to come up, and a lot of things are happening in this direction in our own state. Okay. Coming to the electric mobility, of course, that is the mobility of the future, because we all started with the gasoline vehicle, right, which is still on there, but then people started thinking about a hybrid version of it, wherein you do have a fuel, but at the same time you have an electric storage system that comes along. That's what we call the hybrid electric vehicle, and then mostly these are the battery power is basically used for the smooth running, right? For accelerating and things like that, we use the fuel and then switch over to the other things. And while the vehicle is running, the battery gets automatically recharged. And then we moved on to something called plug-in hybrid electric vehicles, right? For example, the Toyota Prius is an example for that, right? You do have both. And finally, of course, moving to the out-and-out battery electric vehicle out there, completely powered by the batteries, lithium-ion batteries as of now, right? So when it comes to the giga factories, mega factories that you get to hear all these days, right? Huge initiatives all across the world, right, globally, and this is giga factory of the Tesla, and there are several coming up, and in India also, Reliance and various other industries are planning to come up with this giga factories, right? So people move on with something called a power wall, right? So the idea is basically to tell you that the advancement in this techniques in this technology, right? Really scaling up in terms of these batteries and things like that, right? All right. So I think we've had a fair picture of batteries, all the way from mechanisms, the kind of applications that we are interested in, right? I've not really got you through the challenges. It's going to come soon, right? But we'll pause it for a minute and then really think about this question, that are we doing okay, right, in terms of the performance of the battery? The answer is absolutely, it's a big no. It's a big no. Reasons are going to come a little later, right? But take my word for that. So there is a necessity to build better batteries, right? And R&D developments, research and research developments, which is very important, right? And there are multiple ways to build better batteries. For example, I would still go with the existing lithium-ion battery technology, but innovate, right? Coming with some innovations, be it in the form of developing new electrodes, new electrolyte materials, or as I said, use the nanotechnology to improve your performance, right? Otherwise, just enough is enough with the lithium. I don't think lithium is going to work. And why don't we just move on with alternative to lithium, right? There might be a limit to lithium that we cannot go beyond. So can we think of replacing the lithium chemistry with something else? And that's where there's a bunch of elements out there, bunch of chemistry out there in terms of starting from sodium, potassium, magnesium, calcium, aluminum, zinc, and the list goes on, right? They have very similar properties compared to lithium, And I would say that of which sodium stands out, and you really get to see sodium-ion batteries coming in a big way. And especially countries like India have an edge on it, because sodium is abundant compared to lithium, right? So we can bet on it, and technology is sort of getting mature these days. There are lots of companies all across the globe, and even in India there are several startups working exclusively on sodium-ion technology, which also means that it is coming up in a big way, right? We have a lot of projects in our group as well, working on sodium on different aspects. All right. The other thing is, you have an inherent issue with the batteries, because they are good in energy, but they are not very good in power. But especially for applications like vehicular applications, I need both, because I need both in the sense that I need both power and energy to come together, right? So another alternate way is to come up with a hybrid technology. Can you combine a supercapacitor with a battery, right? So it's a hybrid device wherein one electrode is a supercapacitive electrode, where the charge can be stored at the surface in a highly porous material. And the other electrode is a battery type redox electrode. What is the benefit? I get the best of supercapacitor, which means the power is a bit high. I get the best of battery, which means the energy is a bit high. So I'm probably standing somewhere in between the two. Not a bad idea, right? All right. So that's where you talk about it, because I said capacitors are pretty good in power. Batteries are quite good in energy. So I want my future energy device to be something like this, right? Wherein both energy and power is high. And that is a very, very essential requirement when it comes to e-mobility. I hope you get the point, right? And when you're talking to vehicular applications, right? Think about this. It's, as I said, materials are key, right? Now think about it, right? When you're working on materials, battery materials at the lab scale, for example, in my lab, right? You're okay, because the material, the active material that you're taking, 100% you're utilizing it. But the moment you get to the next level, when I say next level, slowly taking to the application front, right? You're making an electrode where your binder is added. Remember the binder that I talked about it? Some percentage, 10% of the weight goes with binder. There has to be conductive additive, which I said, to connect these particles so that they talk each other. There will be current collectors. Then you see the material content goes down by this much. And the moment you make a cell wherein external housing also gets into picture, the material content goes down. And as you move on to the module level, the system pack level, and finally the application front, you see the amount of the active material out there is so limited. Rest of the things are all junk, are unwanted. When I say unwanted, it is not contributing to your energy density. So the point here is, it's so important that you have to worry about the weight of all other components. And that's why you're talking about, the electric vehicle people are talking about bringing in lightweight materials for building their car, composites, right? Carbon composites, right? So that the entire other rest of the weight of the car is so reduced that my energy density and efficiency goes up, right? It's a very important point to be noted, right? And the other thing is, I'm touching upon various aspects. Battery safety, as I said, very important. You get to hear about all these, the scooters, everything getting sort of blown away and blasted, right? Issues are there. Thermal management is a big problem, right? And as I said, we are using this liquid electrolyte, which is sort of dangerous, unfortunately, right? So there can be gas release, and then heat accumulation and combustion and explosion happens. But don't just get carried away by the paper reports that you see for the two-wheelers getting blown away, because most of the time, personally, I would think that batteries are not to be blamed, because it is just the mechanical abuse that leads to this. Because you're just packing, because you wanted to minimize, you wanted to bring down the price of your scooter, electric scooter. So you're not taking much care about the safety, right? So there is no proper thermal management system when they assemble this battery and in the cell level, because they cannot afford to, because if I moment I bring in a thermal management system there, the price goes up, right? So most of these electric scooters comes without that. And maybe it is not fully tightly packed. So any slight hit on vehicle hitting somewhere, the entire thing gets blasted. So nothing, I mean, really to talk about in terms of the battery issues, but then there are other issues also would be, a reason for this whole thing, right? And you talk about an electric vehicle, and then the question here is, as I said, right, you wanted to minimize the weight of the rest of the components of the car, right? So is there a better way to place these batteries? Today, in most of the electric vehicles, the batteries are kept at bottom, beneath your car, beneath your seats, right? Occupies quite a large volume, but that's what is being done, right? Now think about it in a very clever way, right? Is there a better way of placing these batteries, right? Is there a better way of placing these batteries? And that's where this whole concept about structural batteries get into picture. Again, these are some advanced topics. I'm slightly bringing it up. So what do I mean by advanced, what do I mean by structural batteries? Imagine if I am able to build a battery wherein one of the electrode materials or current collector or active material is can be used as a car structure itself on that's what we call it. For example, I talked about carbon fibers, right? A composite of carbon can be used to build the the car, right? Body parts. So can you structurally integrate a battery onto your car structure, onto your car body parts? That would be exciting, because that sort of takes care of the weight, brings down the weight, because your battery is now embedded onto your car, right? Extremely challenging, so to speak, but then I think there's a lot of innovation to happen. So this is a very, very advanced thought which are going on, right? What if the body panels of a car itself serve as a battery? Take this thought home, and then it will be interesting to come up with some ideas if possible, right? Or on a very similar front, for example, people have started thinking about stacking these batteries onto the body parts, like the side parts, or something like that, right? Distribute the load all across, right? And that's where essentially the idea about flexible storage devices, flexible batteries come into play. For example, can you think about a battery which is completely flexible, right? When I say flexible, especially with regard to the automobiles, can I insert this flexible battery in between the parts of the door, right? Across, on top of the panel, right? Rather than storing, or rather than placing the cylindrical batteries, which is very conventional, very traditional way of putting these batteries beneath your car seats, why not I come up with a flexible battery which can run all along the body panel, right? Reduces my weight, right? Increases my efficiency, improves my energy density and whatnot, right? I'll quickly tell you one example, which is from my own work, which I carried out almost 20 years back, right? While I was in the US. So this was very exciting work, wherein we came up with something called a flexible battery, called it a paper battery. In fact, we've taken some carbon nanotube. I'm not going to details about these materials. Somebody's interested, I can elaborate a little later. But then, some carbon nanotubes and, infiltrated some sort of polymer, wherein you have a lot of this cellulose as the powder, and finally came up with a very flexible battery, right? And there was a company started long back in New York, it's called Paper Battery Company. So all that I'm trying to say is, like, these are avenues, these are new opportunities one could think about, bringing innovations in the existing battery technology, for that matter, right? All right. Maybe why not we just take a short break if needed. It's about an hour, I would say. And I'm going to switch on to a completely exciting topic, which is the cutting edge of batteries today, and which is the future of batteries. You can take my word, you can write down some word. Solid state batteries are going to be the future of batteries. Absolutely, no question, right? So we're going to talk about it, but maybe I would say let's take a short break, and I would leave it to Sukesh for that. Talk, Sukesh. Dr. Sukesh, can we stop for a while? If needed?
Yes, sir. I think we can start after 5 minutes. That's fine.
Okay, maybe just a 5 minutes break we'll give, and then we'll resume. Yeah.
Okay.
Yeah, just let me know whenever we are ready to go. We can start.
Yeah. Okay, sir, we can start.
We can start now, right? Yeah.
Yeah, yes, sir, yes, sir.
Yeah. So what I will do is, maybe just for 5 minutes, we can sort of have some discussions if required for any topics that has been covered till now before we resume with the solid state technology. I would be happy to take some questions at this point if any of you have any queries until now. Okay, if not, I will leave it to the end. Yeah. Just 1 second, I'll just. Okay, I hope we're back and the slides are visible. So it's about solid state batteries. So far, in fact, you can look at here. Give me a second. Yeah. So far, I talked about you have an anode, you have a cathode, and there is electrolyte in between, right? Those were liquid-based systems, right? Solution-based or liquid-based batteries. But now there's going to be change, right? The reason which I will tell you about it, you can very well see that there is a solid completely. There's no liquid in it. Reason why we wanted to shift towards solid state is something which I'm going to discuss now, right? Because this particular plot is enough. In fact, this is again a gravimetric energy density plotted with, in fact, the energy density is being plotted here. And you can clearly see that at some point I told you there could be a limit for the lithium-ion batteries. And that's where we are, this dotted line that you can see here, right? This is the limit for the lithium-ion batteries, about 250 watt-hour per kilogram is the limit of lithium-ion batteries, which means like the existing liquid-based lithium-ion batteries cannot go further, right? There's intrinsically, there's a limit. But the point is, what is the target for the batteries for electric vehicles, right? For an electric vehicle, we are somehow looking at around this red line, right? Which is about 700 watt-hour per kilogram, right? That's the the target for an EV. So it is going to be a huge task to come from here to here, from the existing 250 watt-hour per kilogram to something like 600, 700 watt-hour per kilogram, right? That's a big problem. I would call it as an energy limitation. The second thing is about safety, because I said the existing lithium-ion batteries are not safe. Issues because, as I said, you're using a liquid electrolyte, creates a problem. I cannot extend my voltage window because to get the energy maximum, the voltage has to be increased. I cannot increase my voltage because I'm limited because I'm using a solution, a liquid. Because I cannot extend because the liquid, it will start decomposing, the solvent decomposes, gas will be released. The third point is temperature window, because you're using a liquid and I cannot use it beyond a certain temperature, right? For example, the tropical climate like this, you wanted to use the battery at a higher voltage, a higher temperature, or at countries where the temperature goes, to lower temperatures, negative temperatures, right? It's probably it will not survive. So these are major issues considering the present battery technologies, right? Safety, energy limitations, and the temperature range, right? So, and of course, as I said, right, you have this electrolyte, and this is the dendrite that I talk about it. If I use a lithium, the dendrite, and that pierce, the needle-like structure pierce through your separator and short the cathode, right? And that's why you get to see all these kind of things. So from the conventional liquid electrolyte that you see here, you have a cathode, you have an anode, and there is a liquid electrolyte. What if I remove and replace this liquid electrolyte by completely a solid component? Yeah. And that's what we call it as a solid state battery. Now you have two electrodes, anode and cathode, which is separated by another solid compartment, another solid material, which is called a solid electrolyte, right? So what are the advantages? Well, structure is simple because now you can go to higher energy density because I can increase my voltage potential, right? I don't need a separator because the solid electrolyte itself is an insulator. The voltage can be high. When I say high voltage, means it translates to high energy density. It is bringing safety to the device because there is no it's basically non-flammable. No liquid electrolytes in it, so don't have to worry. Operating temperature can be widened, right? And cost also can be brought down, right? So these are the advantages with the solid state battery, and that's exactly the reason why I said these are going to be the future batteries, future of batteries, right? But everything comes with a challenge because now, if you look at carefully, right, the solid state battery, you have a problem here because earlier there were liquid electrolytes, and the lithium coming from one electrode can easily swim through the electrolyte and get to the other electrode, no problem. But now what happens is the following, because you're bringing three solids together. You have an anode, you have a cathode, and in between you have another solid. So the interface between the electrode and the electrolyte, the solid electrolyte, is a problem, right? I've cartoonists like this, right? Let's say this is your electrode anode, and this is your solid state electrolyte, which is a solid, because always there's an interface mismatch, right? So whatever close plus you do it, at the molecular level, there is a gap, right? So that is a problem because lithium ion comes here and then it cannot traverse to the next electrode unless it comes here, then only the circuit completes. So what do I do? This is an interface problem, contact issue. So best thing to do is to sort of engineer the interface using a polymer, right? I cannot think of using any polymer for that matter, because if I use randomly some polymer, the lithium ion might not be able to, transport through this membrane, through this green, whatever colored polymer, right? So it is also important that we fill in or we engineer the interface using a material, a polymer material, right? Which is also sort of ionically conducting, which means like through that polymer also the lithium ion can transport contact, right? That's one important thing. There's been a lot of work going on in that direction. So these are all challenges when it comes to solid state electrolyte. Ionic conductivity, which means the electrolyte or the ions, the lithium ion has to conduct very fast. Stability is the problem. Mechanical stability, interface, as I mentioned, compatible interfaces to be this bunch of such challenges out there when you are thinking about a solid state transition, right? In fact, this is first of its kind in India, our country, that there is a consortium set up to work on the development of solid state battery technology. And this is headquartered, in fact, the center is at IISER Thiruvananthapuram, and I'm heading that center, a national center. And you can see that there are 14 institutions various IITs, right, all the way from IIT Roorkee, then IIT Bombay, IIT Kharagpur, various national institutions, IIITDM, a lot of other institutions are involved. It's exactly what I mentioned earlier, if you remember, right? There are people from physics background, chemistry background, electrical engineering background, right? People with background in machine learning, right? AI, ML, computational, research, right? Device people, right? So we have a very strong team from, for example, IIITDM, Kanchipuram, were the very, very strong in, this instrumentation, right? They're building a lot of things for us. So what I'm trying to say is like, this is the kind of consortium that one needs to tackle this kind of technologies, right? The challenges in this kind of technologies. Center is going quite good, and we are slowly entering into the second phase of this project, and hopefully we should be able to come up with a solid-state battery technology very soon. So those who are visiting, would plan to visit IISER, I would be very happy to invite and welcome you to our center for the solid-state battery development here. All right. So as I said, you have to work on multiple things in order to mitigate these challenges concerning the solid-state technology. For example, I would say I need to worry about increasing or improving the ionic conductivity, for which the material development is key, right? So it's a solid, I'm talking about a solid, so it has to be highly densified. I cannot have a loosely packed material, then, dendrite can easily find its path. So pellet densification is a strategy, right? I also mentioned about this interface, charge transfer across the solid electrolyte and the electrode interface. You have to introduce some layers. You have to bring in some coating strategies. Dendrite is still a problem, right? Dendrite grows from lithium interfaces, right? Wherein you have to, again, come up with some protective coatings. And there is an interesting configuration called anodeless configuration, which I'm going to talk to you in a while. These are some of the strategies that we look at it. And from now onwards, I'm going to slightly, slowly bring in some of the little advanced things, research, bringing in some of the results from our own work, right? Slowly getting to the advanced phase now. But yeah, please note down if you have any questions, we can discuss at the end of the session, right? All right. So I'll just give you some examples. I talked about some coatings, for example, right? The protective coatings or introducing some interlays and coating strategy. One very simple example recently, what we have done, very recently published in Chemical Science. So idea is basically it's a solid state electrolyte that you're seeing. It's a composite solid electrolyte, we call it, wherein you have a polymer, this blue color, what you see in the cartoon, is a polymer called polyethylene oxide, PEO. And wherein you are adding a solid component particles like a garnet, which is again a solid electrolyte component. And you have problem here because you're using a lithium and these kind of dendrites keep forming. And the moment these dendrites forms, you have a cathode at this end which sort of pierces through and it shorts the battery. So what we have done, one of my postdocs, Shruti, what she has done very cleverly is that, she came up with a very interesting approach wherein a simple coating is given. In fact, we add some additives into this, solid electrolyte called fluorine-rich additives. So that decomposes and forms a thin layer all across. You can see that green layer that's schematically drawn here. And that green layer, it's basically a lithium ion-rich layer, sort of a lithophilic in nature. And that attracts the lithium. And what happens is this kind of dendrite formation is sort of killed, right? So that ends up in getting some very interesting results. These are all devices that we make. In fact, this is the polymer composite electrolyte that I talked about. It's a solid compartment. And it is sandwiched between an anode, which is a lithium, and between a lithium iron phosphate, which is a cathode, right? And it forms a device, a solid state device, a completely all solid state device, I would call it. No electrolyte is added here. No liquid electrolyte is added here, sorry, right? So these are some of the directions that are happening, right? I mentioned about the densification of this electrolyte. Reason is very simple, because think about it. This is a TM tomography picture wherein you see the lithium electrode, which is the anode, and you have a cathode here, and this is solid state electrolyte, right? Supposedly it should be a very solid compartment, right? But what happens is you see these white lines appearing. These are basically the lithium dendrites. I said there will be dendrites, needle-like structures, right? This is so solid, and still it finds its way towards the cathode, right? Because this material is not very densely packed. So it finds its way through the gap, and the lithium penetrates like this. And finally, it will touch the cathode and short. So one way to mitigate this is basically, so this is the loosely packed solid electrolyte material. What if we densify this parent material by adding some densifiers, right? This is something that one of my PhD students, Ashwati, is working on, where she's trying to add some oxide materials into this parent material, and that oxide material goes and sits at the grain boundaries like this. And you see, schematically, cartoon, you can see that it becomes much more denser. And then moment it becomes much more denser, you get to sort of get rid of this dendrite propagation like this, right? That will essentially increase or improve your cyclic stability. I can cycle my batteries for much longer time or longer cycles, right? So this is schematically shown here, because I can take the impedance initially, and some sort of sintering happens, and finally this is what happens. These kind of materials which are added goes and aligns at the grain boundary, and basically sort of brings down my impedance. And this sort of densely packed will have lesser pores here compared to the parent or pristine material, right? And how do I test it? Well, don't worry about it, because I'm just taking you through some results now. There are multiple ways of testing it, how good this whole process is. Basically, there is something called symmetric cycling, we call it. We keep the solid electrolyte at the middle and then keep two lithium at both ends and cycle it. What it means is that the lithium is set to go through this electrolyte, come this side, and then take it back to this electrolyte. So how good and how long this can go without any variation in the potential, that's what we call it, right? It's something called a critical current density, we call it. And the battery devices seems to be running quite well when it comes to this kind of dense architecture, right? So these are one direction, right? So that's about solid state batteries. I mean, I can go on and on, but that probably, with the interest of time, I will try to introduce some more topics before I conclude, right? And there is another interesting concept which has recently come up, which is called anode-free batteries, right? We said for any batteries, right, you have to have a cathode, the black one that you see here. You have to have an anode, which is the typical graphite. And of course, there is current collector, which is copper at this side, and which is aluminum at the cathode side. That's a typical architecture for an existing battery, traditional battery, right? That would leave with this energy density of gravimetric energy density of about 250 watt-hour per kilogram, right? Now, the question is, as I said, we need to increase the energy density of the battery. And if you remember very well that I was talking about, I mean, what all ways that I can bring down the size of the battery, bring down the weight of the battery. And interestingly, right, it has gone to such an extent. Of course, now we are replacing with a solid state battery here, solid electrolyte. And interestingly, it has gone to such an extent that now we are saying that, look, I don't need this graphite anode at all. Why not I just get rid of this anode, right? This anode material. Completely take out this graphite anode, just keep the copper alone. And that's what we call it as a sort of a very, very revolutionary concept, called anodeless configuration. I put it in quotes and quotes because terminology is not great from a pure electrochemistry point of view, because there is nothing like a device can exist without an anode, right? So the idea is that anode is limited, because if I were to keep a lithium metal there, I don't need that very thick lithium there, right? So in this concept, what is happening here is this cathode is lithiated because it's a lithium cobalt oxide. It contains lithium. So I will start with just a copper plate there, a copper foil there. There is no other material there. So the lithium from this cathode will come and deposit onto this copper layer. And in situ, it forms an anode of lithium. Very thin lithium layer I can make it. We have a good control on the lithium because I can control the time, I can control the current at which it is deposited. And what it essentially means is that there is a reduction in its volume because I have now removed the entire graphite here. I kept only the copper here. There is a huge reduction in the volume, and which translates to higher energy density for that matter, right? So it's a new thought. Nothing much has happened. Everything working at the research and development level, at the laboratory level. Issues are still there because if I take a simple copper, if the surface is not great, after several cycles, this kind of dendrites will penetrate. So it is important to engineer the surface, right? It's important to engineer the surface by putting some very thin coating onto it and sort of making it smooth, right? So that there is no compatibility issues with the lithium. Lithium nicely comes and gets deposited onto it without forming a dendrite here, right? So that's something called an anodeless configuration. It is important in the sense that, as I said, if you understand it correctly, from a traditional lithium-ion concept where you have a liquid electrolyte, I remove this graphite and place a lithium metal there, which is called a lithium metal battery. You see the increase in the energy density. Volumetric is upper and the gravimetric is here, right? There is huge increase in the volumetric energy density when I come to this kind of anodeless battery. That's exactly what I was telling about. And an anode is in situ formed here to bring this all solid state metal battery, right? You get to gain quite a lot in terms of its performance, especially the energy density. And the moment you have higher energy density, these are much useful for vehicular applications. I hope you remember my numbers that I mentioned a little earlier. That takes me to sort of the last part of the presentation, maybe a little more, wherein we'll come back to lithium metal batteries. What do I mean by lithium metal battery? So what is the basic difference between, at least some of the things, if you go back, some take home, right? I've been talking about lithium ion battery, and now I'm switching off to lithium metal battery. What is the basic difference? In a lithium ion battery, lithium ion is shuttling between two electrodes, right? So you have a cathode, you have an anode. So it is something like I have two shelves kept here, right? It can be a wooden shelf, for example, right? And in these shelves, lithium ions are stored. So all that happens in a lithium ion battery is from one shelf, which is the cathode, the lithium is coming out of that shelf and then moving through the electrolyte and getting inserted or placed in the other shell. Okay, and during the reverse or the charging or discharging, this guy come out of this shelf and goes and sits in the other shelf. So it's a rocking chair. Whereas in the case of lithium metal battery, the difference is that the anode remains as lithium metal. You are not going to use the graphite or any other material. It is just the lithium metal will act as the anode, right? What is the advantage? The advantage is that lithium metal being used, it has the highest energy density, right? So the battery which is made from lithium is going to have high energy density, but then the catch is, why are people not looking at it? Because safety is a problem, because I'm using lithium as such, dendrite formation, all kinds of safety issues are going to pop up. Now, why am I saying all this thing about lithium-ion battery? Because my intention, my aim is to talk about current trends in battery research today. And this is the most current trend happening in lithium-ion battery technology today, that people are now working on lithium metal batteries. Nothing new in it, because the whole story began with this, configuration, because it all started in the early 70s. There they have used a lithium metal as the anode. It was the LiTAS2 battery, which was done by none other than Stanley Whittingham, who was a Nobel laureate. But then what happened is that they started a company called, I think it's Moly or something, with using lithium and polysulfide. But there has been an accident because of this lithium being used there. And since then, people have completely got away from using lithium as the anode. And that's what people talk about, explode graphite as the anode, and wherein the first lithium-ion battery was produced by Sony, and rest is again history, right? So nothing new, but then looking at various new systems that are coming up, you need a high energy density anode material, and lithium is the best choice. But then problem is, the moment I use lithium, there are issues here. For example, let's say these blue ones that you see here are the lithium metal anode, right? So if I use a lithium metal here, there is something called a solid electrolyte interface. It's an interface being formed by decomposition of my electrolyte, which is a thin film form that basically protects your lithium, in fact, right? So what happens is the following. If the surface is not very uniform, there can be a crack in this film. And there is a crack, means all this lithium will start forming as a dendrite. You see this lithium forms as dendrite. And sometimes it gets detached from the surface of the lithium, and it goes as an isolated or dead lithium, which no longer takes part in the cycling, in the reaction process, right? I'll just, if I work this, I'm not sure, let me check it. Yeah, you can see this one. This is actually you're seeing the real picture of lithium dendrite which is forming. You see, right? This is the dendrite that I talk about, and this will slowly penetrate. These are dendritic structures which is growing from the surface of the lithium, and this is the needle-like thing that I told you, that it is going to basically strike through your electrolyte membrane and then touch the cathode. Now, all these this black layer that you talk about, these are dead lithium. You see, these are dead lithium, right? Now, these are dead lithium, and these are going to be not active at all for further reaction, right? And sort of blocks this electrolyte surface or the anode surface also, right? So this is one issue when you're going to use the metal anodes. But then we have to come up with metal anodes, because that's the ultimate anode that you can think about, especially when you wanted to use it for vehicular applications for high energy density. There are other issues, and there are there are several approaches out there to tackle these issues. For example, right, I talked about the SEI. There can be this dendrite formation, but then you can always put a layer, a material coating on top of this SEI, which sort of acts as an artificial SEI. SEI is called a solid electrolyte interface, an interface between the solid and the solid electrode and the electrolyte. Now, if I put such like an artificial SEI, that basically gives a mechanical stability, because even if the dendrites are being formed here, but the top layer sort of suppresses that one, right? That way, it basically helps in getting a better morphology after cycling, right? So these are some approaches. In fact, one could talk about it, right? And coming to the technology, it is still at the lab scale, I would say, right? A lot of hurdles before we actually move on to the market, because we are playing around at the fundamental level, right? Trying to mitigate this dendrite issues, and getting to the next level, coming up with a real device, And finally, to the commercial applications is a long way to go, but I think this is again a future technology so to depend on, because ultimately one has to live with alkali metal anodes if you were to get to the energy density that we were talking about, something like 700 watt-hour per kilogram, which is required for your vehicular applications, right? Okay, right. I would take one example again to talk about the strategies that we, we've recently reviewed this whole area in a very recent paper. Last year, we published this paper, the strategies to develop stable alkali metal anodes for rechargeable batteries. You can see that, right? Wherein we have discussed various aspects of this whole technology. And I would just give a couple of examples from a very recent efforts from our lab, a little bit on to the research side, right? So I'll try to make it in a very simple way. So please understand this. From here onwards, my motivation is to come up with a very thin anode, right? It can be a very thin lithium onto my copper, for which I'm taking some steps. So in this effort, this is done by my PhD student Rajesh, who led this work, and he started with a copper foil, right? Using a chemical vapor transport, he takes a selenium, and that selenium is transported onto this copper, and you get a copper selenide, which means like the top portion of the copper reacts with selenium to form a copper selenide on top, right? You do all sort of characterization using XRD, scanning electron micrographs, all kind of things that you do. It's a very flexible film. You can see that, very flexible, right? And then what we do is we let it react with lithium. And the moment it reacts with lithium, it forms a layer which consists of lithium selenide plus copper. And that's the black layer that you see here. And that's where I talked about something called an artificial SCI layer, which is formed on top, right? My idea is basically, as you use this as an anode, the lithium is going to come, and what happens is this black layer that we talk about is so lithophilic. It's so compatible with lithium because there is this element called Li2Se complex, which likes lithium. So lithium comes through it nicely and gets deposited onto the copper, which is beneath, right? So which means like all my lithium is now very well protected because there is a top layer of this black layer, right? So any such issues, further reaction will not happen because this black layer kind of protects it, right? And we do a series of tests. I'm not going to details about it, but all that indicates is that this modified current collector works well, right? There are systematic ways of looking at it, how good your electrode, how good your coating is, by looking at the nucleation potential and so on and so forth. I'm not going to details about it. Finally, we built a cell. We built a device which is using very limited lithium, sort of closer to anode-less configurations. Very thin lithium is being used. And we made a battery. It's called a limited lithium metal battery. And you can see that, right? This is the cycling stability. You can see that we have cycled about 200 plus cycles. And the blue ones are our modified electrode, which seems to work pretty good in terms of stability. Whereas the red one, which is just the copper, dies out at a much early cycle number, right? And this is a typical power capability testing, which we do at a different current rates, right? And you can see that the blue ones, which is a modified one, works pretty good at very high current rates, whereas the red ones, which is the pristine one, sort of dies out, right? And similar things, we have done it for sodium. I mentioned that sodium ion is picking up in a bigger way. And similar anodeless configuration has been also studied. This is being done, another student of mine, Nilesh Pandey, wherein he has been looking at different coating technologies for sodium-ion batteries, wherein he has now taken a copper, which is a current collector, and he tried to modify this current collector using another material called an oxychloride, an indium oxychloride material, that also forms a sort of artificial layer like this. And this is what I said a bit early, that remember, you form this layer, and then any sodium which is coming or lithium which is coming nicely goes through this material film, and it gets deposited onto the copper. And the sodium or lithium is very well protected by this layer which is coated, right? And that basically gets sandwiched in between the copper and this modifier film. That's our approach. And that has resulted in very good, interesting studies. We have looked at the, what do you call it, the interface or the cross section of these film, and you can see that lithium, sodium sits here and all kinds of things. And with a collaborator from IIT Bhubaneswar, we have done some computational studies also to sort of understand how the sodium is getting transported here, how well this layer sort of protects our sodium in this matter, right? These are some details about this work. And ultimately, we've shown that these are interesting approaches that we have undertaken, right? Another technology is about lithium sulfur battery. I don't know how many of you are familiar with the sulfur techniques. All that they use here is a lithium anode again. I told you lithium anode is something interesting because of its high energy density. And the cathode is sulfur, right? The mechanism are quite different here. The advantage is that, I'll list out some of the advantages here. The advantages here, the capacity is quite high, 1675 milliampere hour per gram, and energy density is almost 10 times what we can get now. Remember, the existing lithium-ion battery has a energy density of about 250 watt-hour per kilogram, whereas if you use a sulfur battery system, it is going to give you something like 2600 watt-hour per kilogram, which is absolutely exciting to work in this area, right? But having said that, there are sort of issues. Drawbacks are quite large, in terms of the polysulfide dissolution. All kinds of things are happening here. These components dissolve in the electrolyte and gets deposited onto the anode, which makes anode more reactive. There is loss of capacity. All kinds of issues are there, right? Which are yet to be tackled, right? There are multiple ways of addressing that. Embedding the sulfur in a carbon matrix, and so that the sulfur is sort of protected, right? Trapping this polyselenide using a sort of a membrane, as you can see here, right? This is something that is ongoing in our lab as well, working on multiple aspects of it, right? And yet another type of technology is called dual ion batteries, wherein two ions are taking part. So far, I've been talking about only the transport of lithium ions, shuttling between these two electrodes. Here, what happens is, like, I have a graphite plate here, graphite plate here. It's a new concept, relatively very new concept. And now, in an electrolyte, liquid electrolyte, you have lithium ion and anions are also present. It's like you put a salt, NaCl, for example. It's gets split into Na plus and Cl minus, right? And what happens is, like, in a single go, these respective ions will go towards the respective electrodes. For example, the positive ions, these are cations, the lithium ions move towards this anode, whereas the PF6 minus 1 moves towards the cathode because they are negatively charged. So that's a very simple way of using it. Advantage is, like, I can go to much higher voltage, right? This is again a new concept. And a lot of optimizations are to be carried out. And interesting, I also did not mention about this, that a lot of AI ML is being utilized, being introduced in the battery technology, right? Wherein, much of the work can be sort of listed out, right? Sorted out, especially when it comes to the multiple permutation combinations that are that are available here, right? Different combinations of the electrolyte, different combinations of the ion, things could be sort of sorted out. For example, in a very recent studies, we have, my own group. Well, I mean, I am not very expert in this, but then, I got a student, very interesting student, Bibin. He's actually a mechanical engineering background. He's a BTech with mechanical engineering from NIT Calicut. So he sort of joined our program on integrated PhD. And he approached me saying that he's interested in batteries. I was a bit confused initially to take him, because usually I will have only students from physics or chemistry background joining me. And then this is the first time an engineering background, that too from mechanical engineering, approached me. I said, okay, let us give it a try. And he joined. And fantastic, with all this expertise on various aspects of engineering device, he did a great job. And he just graduated last year. So he's the one who came and said, like, why don't we do some machine learning, right? I said, I have absolutely no background. He said, no, I'll work on it. So he came up with all this interesting studies, and he's the one who worked on this battery, dual end battery, and did a bunch of things on using this AML. And these are some of these results, right? So he predicted a lot of things in terms of the combination of the electrolyte, in terms of the voltage window, in terms of power and energy densities, right? So that was very interesting. And, we're continuing from where we stopped. And, we get some of the works done using our undergrad students. They're quite, good in these topics. So, all that I'm trying to say is like, AIML is something picking up in a big way in battery technologies as well, right? And the last one is about batteries recycling. I'm not going to talk much about it, but just to complete the story, right? This is something that I've been telling. Imagine in another 10 years, right? The roads are going to be filled with more battery-powered vehicles, more to see two-wheelers and three-wheelers in India, right? And that's the market that we are always looking at, in fact, initially to supply these batteries to. But no one knows what's going to happen, right? The reason is like how there's going to be a lot of waste coming up, battery waste coming up, right? And going to be a tricky situation. Nobody knows how to handle it. That's one aspect, right? The question is like, can we recycle these batteries, right? The motivation is multifold, in fact, right? Because we are going through, this is what I started my talk, right? Because indigenization of the battery technology is the need of the hour, right? Right now, as a country, India is depending on almost everything for the battery when it comes to battery materials, right? The nickel has to come from outside, the cobalt has to come from outside, lithium has to come from outside, and even the casing, a good casing has to come from outside, right? So everything we are depending on other nations, right? More importantly, for any countries globally, all these elements that we talk about, starting from lithium, nickel, and cobalt, these are all critical minerals, right? And even the graphite that we are using in our lithium-ion battery, that is also a critical mineral, right? So how are we going to tackle this, right? Do we have enough technology to sort of come up with our own methods to, get these minerals, right? The question is no, right? And that's where we depend on recycling of the existing batteries. There are multiple ways of doing it. One is the traditional recycling, which involves quite a lot of metallurgy. And the other one is, which is more, popular now, which is called direct recycling, wherein, you take the spent batteries, take it apart, take the cathode. The cathode will essentially have lithium, nickel, cobalt, depending on what electrode, what material it's made of, right? You do some process, okay? And basically what you're trying to do is restructuring the cathode, because the lithium cobalt oxide, because these are all spent or dead lithium cells, right? Each would cycle for n number of cycles. And during that, the lithium content would have gone. Structurally, there could have been a lot of issues. So what people do is, right, they try to restructure it, for which they have to give some additional lithium, because lithium would have come out of it, additional lithium, and restructuring, re-lithiating and restructuring to a new cathode. That's one way to do it, right? The other method is basically, you can actually extract several things from it. For example, lithium can be extracted as an element, cobalt can be extracted as an element, and not just that. In a very recent study from our own group, it's again done by my PhD student Rajesh, what he's done is very interesting, right? He took a battery like this, right? Removed it, cut open, removed it, he took the spent cathode, which is a lithium cobalt oxide. And what he did is taken out this one, right? Added some metal sulfate solution in it. Simple chemistry. You can imagine the amount of chemistry that I can afford to. I'm from a physics background. So very simple chemistry. So it gives you lithium sulfate, and then finally, using a carbothermal reduction, he gets something called lithium sulfide. Right? So instead of getting the lithium cobalt oxide restructured and using it for a lithium-ion battery, what we have done is very cleverly, using very simple reactions, from a spent lithium-ion battery, from a spent cathode, we were able to get this lithium sulfide. And this Li2S is a cathode for a lithium sulfur battery. Right? So that's an exciting approach. Actually filing a patent for that. It's a very new work. I'm not supposed to talk about much details about it, but I thought I'll just mention this, right? So what we're trying to now do is, using that recycled material, we built an anodeless sulfur battery, wherein I have a copper here and this recycled lithium sulfide is here. Fantastically working battery. And believe me, we have not taken a single lithium from outside. Right? It is completely from a recycled battery. Entire lithium is now taken. Now this lithium from this lithium sulfide is settling and the battery is working well. I don't know, I have a picture, but he has just shown me that he has powered a tiny timepiece using this battery, a coin cell battery that he has made, right? So a lot of things happens around this, right? I think I would stop here. A lot of things are happening around this, and what I tried to give you today is an overview on the current trends in the battery technology. So just to sum up, all that I've tried to do is, starting from the basics or fundamentals of battery technology, in particular on lithium-ion battery, how does a lithium-ion battery performs, the mechanism of working principle, right? Then we moved on to talk about various aspects, especially the various energy domains that are important. I emphasized a bit on the micro batteries. There's a huge R&D gap in micro batteries, right? Companies are slowly coming up, market is booming up, right? But unfortunately, the technology needs to be a little more matured in that direction. A lot of challenges, a lot of people, including our own group, are working towards building efficient micro batteries. Then I moved on to talk on the other aspects, touched upon a bit on the flexible battery, the need for building flexible batteries. For example, I can think about using these flexible batteries as car panel doors in between that, sort of takes away the weight and improve the efficiency and the energy density of a electric vehicle, right? And I also talked about various other alternative chemistry like sodium-ion battery picking up. And after the break, we started talking about the solid-state batteries, which is sort of going to be the future of technology. It's already there are commercial batteries, solid-state batteries out there, and slowly the e-vehicle electric mobility is going to completely be taken away, ruled by the solid-state battery technologies. Toyota has invested millions and billions of dollars into it, all the way from 2008, 2010 onward. They've been pumping money. So there is a huge market out there, and believe me, solid-state battery are going to be the future technologies. And also we touched upon something called anodeless batteries, a very interesting concept on anodeless batteries. And last but not the least, I did mention about the recycling, the importance of recycling. Again, sort of the need of the hour, because we've been talking about e-vehicles switching completely, transitioning to a e-mobility, but then one has to worry about the environment as well, right? So how prepared are we, down the line, another 10 years, when it comes to recycling batteries for that matter, and also to realize this, the indigenization of the technology is also important, right? When it comes to the battery technology as well. So with that note, I would end here, and would be very happy to take some questions from the audience. So for the sake of it, I'm going to stop this sharing, right? And we'll move on with this. Yeah.
Shaiju sir, it was a very interesting talk. In fact, just to remind the audience, the cruciality of this battery technology, you can see that maybe 5-6 years ago, the average life of the battery was about 5 years or so. Recently, nowadays, the new batteries and all, the average life of the battery is about 8 years. So actually, if you look at the technology side or the economic side, battery is in fact a very crucial bottleneck to us when we are thinking about maybe solar systems or so. Say, for example, if you invest on one kW or 1 lakh on a solar system, almost 50% of the cost will go for the battery. So whenever this will become economical, unless there is a very drastic change in the technologies or very drastic improvement in the technology side of the battery, especially the chemistry side of the battery. So in this context, the talk rendered by Dr. Shaijumon is in fact a very interesting and a very enthusiastic talk, because in fact when he talked about the anodeless battery, normally we always conceive a battery as an anode and a cathode and an electrolyte and so on. So an anodeless battery is a very interesting portion there. And moreover, the recycling part, recently when I read an article, it was about, they were mentioning that about 30 million vehicles will be plying the roads of the world by 2030, which are electric. So every electric vehicle will definitely have a battery component. And what to do with these life blown away batteries? So those are very crucial things that we need to look into when we when we are thinking about an environmental perspective as well. In fact, if you look at the papers that Shaijumon sir's group has authored, I just had a glance last day on the papers. It is in fact a very interesting read. So I request the participants to go through the papers there and the research work that is being done in the group. So in fact, we are very happy to have you here, sir. So dear participants, I would like to ask each and every one of you to interact with him, because this is a very rare opportunity that you get such a very good researcher in such a faculty development program. So please ask the relevant questions and interact with him. The floor is yours. Thank you.
Thank you very much, Dr. Sugesh, and it's very well said. I'm so happy to hear that we have summed up very well. Which is to the point. Thank you very much. Yeah, please, very happy to address some questions. These are something which we do on a routine basis, and right at the heart. So would be very happy to listen to you and then address some questions. Yeah, I can. Dr. Sugesh has asked me for the presentation. I'll probably remove a bit of it due to IP issues, but rest of the things, excluding some of the unpublished work, yeah, I'd be happy to share the slides with Dr. Sugesh later today. All right, maybe looks like there are no questions. So no problem. So, but feel free to write to me. If you have any questions or queries. So I'll be very happy to sort of address that. And do visit us at IISER, and whenever you're coming to Trivandrum, just I have my contact details are with Dr. Sugesh, and you can always call me or message me or write to me. I would be very happy to host you at IISER, and we have a wonderful campus. We have a very active research going on in this area. So I'm sure you would like to come and have a look at these things. Yep. All right. So I think that's the okay. Fine. Yeah, Dr. Sugesh, anything else? I'm not sure that there are questions in the messages. Just have a look at it. Not really. Okay. I'm surprised. I thought there'll be a lot of questions. The kind of talks and lectures that we give at IISER and all, like the moment I open my mouth, I'll be bombarded with questions. So that's where we are trained to address. That's fine. So yeah.
Even recently, Shaijumon sir had a patent. You had a patent, right, sir? Regarding
we
that,
had a patent.
Yeah, a small kind of battery which you nano battery or something like that.
Yeah, there was one nano battery we had. Yeah, that was that's what I was talking about, the micro battery. So
Yeah.
So
dear participants, please interact actively.
And we had another one, in fact. So I keep telling, when I talk to the students, especially the school students, this is one thing I talked about. At least, our stage, our age, we've been told that the kind of research that the so-called scientists do, that these are for the next generation. So that's this kind of thoughts we had when we were growing up, right? So these people do it for the next generation. But this is my own example, because one of these works which was done while I was in the US, that's what I talked about, the paper battery. It's a flexible battery. And apparently we had a US patent on that. And then we came up with a company which is called a paper battery company. So it would be interesting. The prototypes have come, and then unfortunately there were some issues with the funding and things like that. But think about it. You're trying to buy a battery from a shop, and then the shopkeeper keeps telling you all kind of things about this flexible battery and this that, and then interestingly you are at the other end, who are one of the inventors of the battery, and it would look so interesting, and it's a level of motivation that I can probably impart or give to the students. I keep telling this to the And these days, that's what's happening. You just come up with some technology, and then the support system is so good. And the moment you have some better, technology, I'm sure you're all from engineering colleges and institutions, wherein a lot more ideas are popping up, and there is a lot of this, support in terms of the ecosystem for the startup in India, and especially in Kerala. Right, a lot of incubation centers out there. You just come up with, there are people ready to invest on you. VC concept is becoming a big deal here, right? And our own technology that I just mentioned about this recycling and the lithium sulfur. In fact, my student said, we wanted to take it forward as a startup. I said, why not, right? So yeah, you need to get some very brilliant, smart students at the same time to take things forward. So all that I'm saying is, like, this is something, the gap between the invention and the final commercialization has so reduced these days, right? So within few years, things are going to get to the market, and then that's a great feel that you get, when you get to see this things going in that direction. Set apart the fundamentals or the fundamental science that is involved, which sort of drives you forward in this whole thing. Yeah.
Sir, good evening, sir. So,
yeah, good evening. Good evening. Yeah.
So my name is Kannan. I am from LBS College, Kasaragod.
Okay, great. Yeah.
So I don't know this question comes under this category or not, because whenever different batteries are used for different applications, there is a challenge to find out the state of charge behind this, right? State of charge for a particular battery when it is working under real-time condition.
Yeah.
Whether that differs for different batteries, the concept to find out the state of charge.
Yeah. So the answer is it done? Your question is done?
Yes, sir. Yes, sir.
Okay, so very interesting, very nice question. So, certainly the state of charge is going to be different with different chemistries and different technologies for the matter, because conceptually the mechanism of charge storage is also going to be different, right? See, for example, the lithium sulfur battery, I did not go in details about it, because the voltage that you talk about is much reduced, around 2.1 volt. You will get it for a lithium sulfur battery against what you see around 4 volt that you see in the case of 4 volt that you see in the case of the normal lithium-ion battery. So everything going to be different. The state of charge and the depth of discharge is all going to depend on the chemistry that you talk about it, certainly, right? And there are ways to detect the state of the charge. Individually we can look at that, and then and that's one way to analyze it also, right? Because every this cycling that you talk about is typically, we say 80% of the charge is something that we are okay with it, right? When we say that, always that we look at it, right? It took in 100 cycles or 1,000 cycles, I could get to the 80%. That's the benchmark that we give in terms of analyzing these cyclic stability of the batteries out there. Yeah, so the answer is yes, it is going to be different with the different chemistry that you get to see. Yeah.
So whenever we study the case of a state of charge, whether that is when we are doing the research, whether we need to take the case of charging cases as well as discharging cases, that is how particular a battery gets charged, or
we look at both state of charge as well as the depth of discharge, depending on what you are looking at it. For example, all that I can say is, I'm not very sure about how people are doing it at the industry level, but at the lab scales, we do that, especially when you wanted to, especially in this case, when you wanted to really look at, what is happening. For example, what I do is, the state of charge, we look at it. In fact, we charge or discharge, or let's say we charge this battery, and you can real time monitor where that state of charge is, basically, because it will be real time. The voltage will be varying with respect to time, and I can pin at a particular point. And I might be, as a fundamental, for the fundamental interest, I might be interested in really understanding what really goes there. For example, there might be a reaction happening, and that's where I get a play to. So at that particular point, when the voltage reaches at that particular point, I'll pause, right? I'll stop the experiment. And when I stop the experiment, there'll be slight variation in the voltage. And then what I do is that battery, which is typically a coin cell battery, we do it. And we take it inside our argon-filled glove box and open the battery, cut open the battery, and take out the material, clean it up, take out the material, and then there is some load lock things are happening, and then we take it directly to investigation. There is something called various spectroscopy techniques are there, like X-ray, photoelectron spectroscopy. Will exactly tell you, right, what are the details there. Yeah, that's what we do.
Thank you, sir. Thank you.
Any other questions or comments or anything you wanted to share?
Okay, so if we don't have any other
No, 1 second, Dr. Sugesh, I think there's a comment which came from Matthias PSC. So there was this comment, maybe I can read it out. Please answer, the electric vehicles become hazardous after their lifetime. How can these batteries be safely recycled? Yeah, I think that is something that we have been mentioning. I think Dr. Sugesh also mentioned about it. Yeah, this is going to be a serious issue, right? So these are going to be certainly a dangerous, hazardous waste that's going to pile up. And that's where the recycling business has to come. And there are a lot of groups out there who are working on it, safely recycling it. It can be an upcycling also. Recycling is restructuring and using it for the same material. It can be upcycling also. In fact, we have published some time back wherein this lithium cobalt oxide is used, we recycled and converted into cobalt oxide, CO3O4. And we found that this cobalt oxide is interesting as a supercapacitor electrode. Right, so that's what we call upcycling. Not necessarily you have to recycle and use it for the battery applications itself. For example, if I can use it for something else, let's say as a catalyst to develop or generate hydrogen, that's also equally good, right? Yes, it is possible, and a lot of work is going on in that direction as well. Okay, if there are no other questions, again, feel free to write to me if you have any queries in this regard. Otherwise, let me take this opportunity to thank Dr. Sugesh and his colleague and his team as a whole, first of all, for organizing such a very important, organizing an FDP on such an important topic like this, and having, invited me to talk about some of our work and as well as the batteries as a whole. Yeah. Thanks again, Dr. Sugesh, for the opportunity. Thank you all for listening to me during this.
Yeah, thank you so much, Shaijumon sir, for being a part of this program. I would request Agil Chako sir to give the concluding remarks.
Good evening, sir. First of all, thank you for your wonderful session. I think all the participants will gain some basic idea, because every day we are hearing something like this electric scooter or fire hazards and something like that, and the battery chemistry is having an impact on that. So I think personally, I think the session was very good and very informative. So being an engineering background, normally we will not see into the materials and all other things. So so very interesting session, and thank you for your time, sir. And so on behalf of again department and coordinators of this FTP, very much thank you. Sir, thank you very much.
Yeah, thank you all. Thank you very much. I'll probably log off now. Yeah. Thank you once again. Yeah, bye-bye. Thank you all and good night. Yeah, bye-bye.